is what we are going to be talking about today. So power is actually going to be our last formal equation that we're going to be introducing to you. We're going to take a little bit of notes, talk a little bit about what power is, what it does, all that jazz. And then we are going to introduce that equation. So before we start, we're going to talk about different types of batteries. Okay, so there are tons of different types of batteries you could buy. If you go to the store, you might see AA, AAA, C, D, 9-volt batteries. Then you also see like watch batteries and things like that. Some of those batteries have different voltages, right? So if you look at them, if you look on the label itself, you might see what the voltage is. If you don't see it on the battery, very typically you'll see it on the case that the batteries come in. And remember that voltage or potential difference is essentially that force pushing the electrons around the circuit. So the higher the potential difference, the stronger that push forcing those electrons to go around that circuit. The smaller the potential difference, the softer, the more gentle the push that's causing those electrons to go around the circuit. So 9-volt batteries have 9 volts available. And then our typical batteries that we use are AA or AAA or C and or D. Those are all 1.5 volts. So one of the reasons that we might see or use different batteries is strictly just because there's different voltages. But what you might see is, well, oops, I didn't want that. I want freehand. But what you might see is our AA or AAA or C and or D batteries, they all have the same voltage. So what's the point of having different types? Well, first of all, if we have a different voltage in terms of batteries, if we were to connect this into a circuit, so we connected this with a wire to the light bulb and back to the battery, our electrons would flow from negative to positive, and this light bulb would shine brighter than this light bulb at the top. The reason being is that this voltage is 1.5, whereas this voltage is 9. The battery with the higher voltage is having that stronger push, causing the electrons to travel faster through the circuit, which causes this light bulb to shine more brightly. So obviously a battery with a higher voltage will cause the light to shine more brightly, which is why you might want batteries with different voltages. But again, back to the question, why would you want different types of batteries if they have the same voltage? Well, if we take a look at our batteries that we were talking about before, our AAA or AA or C and or D, those all have the same voltage, right? Our AAA, our AA, our C, and our D all have 1.5 volts in terms of a potential difference. The different size of the battery, what that does is it actually allows them to store different amounts of energy. Okay, so we could see that our AAA battery is the smallest. Then we have this AA, which is a little bit bigger. Our C, which is again quite a bit bigger actually. And then our D, which is just this huge Mongo battery here. Okay, so the difference between them is the size. And what the different size allows for is that each battery will be able to store different amounts of energy. Okay, so the larger the battery, so if we're looking at like a D battery compared to a AA or even a AAA battery, because the D battery is larger, it will have more storage space for energy. Whereas the AA being smaller will have less storage space for energy. What that means, what does storage space for energy mean? That just means how much longer it will last. Okay, so a D battery will last much longer than a AA battery. Okay, in terms of like, hey, how often do I have to change my battery? They will both give the same amount of potential difference, just the larger battery will last longer. Okay. And when we take a look at it just in terms, a little bit of comparison-wise, but we're not necessarily going to be using that, or these units here. So AA batteries will have about 1,000 milliamps of hours for storage, whereas a D cell battery will have 8,000 milliamp hours of storage. Okay, the whole point here is not to necessarily notice the units, but just notice that this one, their D battery, is 8 times, it will last 8 times longer than our AA. Okay, so that's what the size difference does. So even though the voltage or the potential difference is the same, our D battery will last 8 times longer than our AA battery. Okay. So we talked a little bit about energy, right? How much storage space it has for that energy. And we're actually going to take a look at an equation that relates electrical power and energy and time together. So electrical power, power, is the amount of energy, that amount of electrical energy that we convert into heat or light or sound or motion every single second. Right? And remember that in the previous lesson about resistance, we introduced the word called loads. So a load is just anything that converts electrical energy into something else. So for example, a light bulb was a load that converted electrical energy into light energy. We also talked about a toaster converting electrical energy into heat energy. We also talked about a fan converting electrical energy into kinetic or mechanical or motion energy. And we also talked about TVs and computers, and then they converted our electrical energy, computer/TV, into both light and sound energy. Okay? So electrical power is the amount of energy that's actually being converted by that load every single second. So here, we're introducing 2 variables. We're introducing power, we haven't seen that before, and energy. Okay? Time, we know what that is. So here we have P stand for power, E stand for energy, and T for time. But we've already seen time in our current equation. So power is actually measured in watts. Okay? So that is represented, the units for powers is watts, and watts is abbreviated by the capital letter W. Energy is measured in joules, and joules is abbreviated by the uppercase J. And time, as we know, is measured in seconds. Okay? So if we're ever given values that aren't in watts, aren't in joules, or aren't in seconds, we might have to do a little bit of converting first. But that is something we're more than capable of. We're a smart bunch. Okay? So this is a formula, again, that you will be provided with. Just like the other equations, we might sometimes have to rearrange it. Because maybe sometimes we're wanting to find energy, or we want to find time because we're given power. We might want to rearrange that equation. And again, we could use our little triangle trick here. Okay. Notice when we're looking, I'll just erase this little box. Notice when we're looking at this formula, we have P is equal to E over T. So we see that E is on the top and T is on the bottom here. So similarly, in our triangle, we have to put E at the top and T on the bottom. And then P, our power, takes up that last remaining space. Okay. The way the triangle works is we cover up the value we're trying to isolate, the value we're trying to get alone. So if we want to get P alone, here, I'll zoom in here. We cover up P, and then we're ending up with E divided by T. And that is the formula that we were actually given, but it's nice to know that the trick still works to give us the original formula back. If we want to figure out what E is, we cover up E, and we're left with P times T. So E is equal to P times T. And if we want to find out what T is, we cover up T, and we're left with E on top of P. So E divided by P will give us our T value. T is equal to E divided by P. Okay, so these rearrangements, again, you will only get the original formula. You'll get this guy here. But using that triangle trick, you can go ahead and figure out the other two rearrangements if you would like. Okay. Alrighty. Something interesting here is that when 1 joule of energy is converted into light, heat, sound, movement, etc. every second, then the power of the light bulb is going to be 1 watt. What this says, if we're looking for power and we know that it's 1 joule, 1 joule every 1 second, 1 divided is 1, so our power will be 1 watt. That's essentially what that sentence here says. Okay. So we are going to look at the words energy and power a little bit more, because in everyday English, we often kind of use power and energy interchangeably, but they don't actually mean the same thing. Okay. So energy, what that is the ability to do work. So if we're thinking electrical energy, what is that electrical energy capable of, right? It can change into light energy. It could be changed into heat energy, sound energy. But energy itself is just the ability to do some sort of work. And it's measured in joules, which is our capital J here. Power is the rate in which that energy is done, or the rate at which the work that energy is able to do is done, right? So how fast the energy is consumed over a period of time. That's why we get our formula. Okay, well, first of all, it's measured in watts, which is a capital W. But that's how we get our formula. Power is the amount of energy that's consumed over some period of time. Another kind of cool thing about power, we don't actually introduce this formula quite yet, but power is actually just a combination of voltage and current. Okay, so voltage and current together give you electrical power. The bigger the voltage and the bigger the current, the more electrical power we have. So again, what I'm about to write down is not a formula that we're introducing in this lesson per se, but something kind of cool if you want to relate it to some of the concepts that we've already looked at. Power can also be calculated by saying, well, I have my voltage, or my potential difference, and I have my current. Those two things together, how big that push is and how fast it's moving around my circuit, well, that will also give me my power. So my power could be thought about in one of two ways. The way up here is the one that we're focusing on in this lesson. But it's kind of worthwhile to note that it is possible to look at power in a different way. Okay. Power is very often expressed in watts, but sometimes we see kilowatts. And K, a lowercase k in front of a W, represents kilowatts. And 1 kilowatt is the same as 1,000 watts. The way that I remember that is the prefix kilo is similar to like kilometer. And if I ran 1 kilometer, that would be saying I ran 1,000 meters. Similarly, you could see that if I have 1 kilowatt, that's 1,000 watts. Right? So that's kind of an interesting way that I like to kind of remember it, just because sometimes it can get confusing. So if that helps you too, awesome, awesome, awesome. If it doesn't, then whatever method helps you remember, then awesome, great. All right, so we're going to look at a couple of examples, and then that's going to be it for today's lesson. So again, just like every time we use that equation or any equation, we go through 4 steps. We write what we know / what we have / what we want on the left-hand side. Step 2 is we write out the equation we're planning on using. Step 3, we're going to plug in all the values we know into our equation. And step 4, we're going to get a final answer, plug things into our calculator, and then use our final answer with units. Okay? So here we have an example about a light bulb. And a light bulb uses 83 joules every 60 seconds. What is the power consumption of the light bulb? So we know we have 83 joules. We're given 60 seconds. And we're trying to look for the power. Okay? So step 1 here is we're going to write down everything we know, everything we're trying to find. So we have 83 joules. And the value that is measured in joules is energy. Okay. We have 60 seconds. And 60 seconds is a measure of time. And we're trying to find out what power is. And we don't know what it is now, but we know that its final units will be watts. Okay? Step 2, we are going to write down the formula we're planning on using. And so that will give us our equation that we were given originally. Our power is equal to our energy over time. Right? It's isolating for that P, that power, so we don't have to rearrange anything in this first example. Our third step is we're going to plug in all of the values for all of our unknowns. So E is actually going to be 83 joules, and time is actually 60 seconds. And for step 4, we're going to plug that in. So we're going to go 83 divided by 60, and we're going to go to 2 decimals. So we have 1.38, and if you look at your calculator, it should just say 3, and so on and so forth. To round to 2 decimal places, we actually take a look at that third decimal place. It is a 3. Because it is a 3, we round down. So we will get 1.38. And we need final units here, and our units for power is actually going to be our watts. So, So we should get 1.38 watts. That is the power consumption of the light bulb in this example. And again, we're going through all these steps. Step 1, we write everything we know, what we're looking for on the left-hand side, because again, that can help us figure out what equation we want to use, especially when we get to a point where we're not just looking at one equation at a time. At this point, we have actually introduced 4 equations already. So if I give you a question like this, in this specific setting, yeah, we know it's going to be the power equation because we just introduced it. Of course, we're going to practice with it. But down the road, maybe something in terms of an assessment or a practice worksheet or something like that, you might not be told which one you need to use. So the step 1 is going to be super important in helping you figure out what we need. We need to use an equation that has E, T, and P all involved. And of course, that is this equation here. Okay. Step 2, we tell me what equation we're using. Step 3, we plug in our values. Step 4, we have a final answer with units. Life is good. Alrighty. Example 2, we have a hairdryer and it uses 4,000 watts. How much energy will it use if it runs for 3 minutes? Alrighty, there's some fun stuff going on here. Again, step 1, we are going to write out what we know, what we're looking for, all that fun stuff. We have 4,000 watts. And what is measured in watts? Of course, it is power. Next, we have 3 minutes. Okay. 3 minutes is going to be our time, but kind of an important thing here. Time in our equation has to be measured in seconds. Okay, which means we cannot use that 3 minutes. To get minutes into seconds, we know that every minute has 60 seconds in it. Oh, that rhymed. So 3 minutes will be 60 plus 60 plus 60, right? Or you could say 3 times 60 seconds in 1 minute will give you, 3 times 60, will give you 180 seconds. Okay? So if we are ever given a value that is not in our standard units that we have to use, we do have to do that conversion. 3 minutes is not going to be sufficient for us because we can't use minutes in our equation. Our equation's only dealing with seconds. So we have to convert. Okay. Sometimes people have trouble like, well, am I dividing by 60 or am I multiplying by 60? Right? If you know that in the end, if you're comparing seconds to minutes, you should have more seconds than minutes. The value for seconds should be bigger than the values for minutes, right? Because 60 seconds is the same as 1 minute and 60 is bigger than 1. You should be able to go ahead, multiply or divide, but ask yourself, does this answer make sense? Right? If I took 3 and I divided it by 60, I would get 0.05, and it doesn't make sense to have 0.05 seconds in 3 minutes? No, not quite. Okay. Any hoozles. The last thing is we're trying to find out how much energy it will use. So we don't know what E is. Oops. But we do know E should be measured in joules. All right, step 2 is we're going to figure out what equation we're going to use. Of course, we are given this equation here, but we need to isolate for E. So we're going to use our little triangle trick because E is on top of T. There in the equation, E goes on top of T in my triangle. T takes the remaining spot. To solve for E, I cover it up with my finger. I'm left with P times T. So I get E is equal to P times T. And that is the equation I'm going to use. So step 2, I should get E is equal to P times T. Step 3, I am plugging in the values that I know. So instead of P, I'm going to write 4,000. Boop, boop, boop. And instead of T, I'm putting in 180. Not that 3 because I can't use minutes in my equation. Last but not least, I go ahead and I multiply with my calculator. I go 4,000 times 180. And that, ooh, what's that big number? Should give me 720,000. And my units are joules. So for my energy, well, that's kind of an ugly box. For my energy, I get 720,000 joules is how much my hairdryer will use in terms of energy if I run it for 3 minutes. Okay. Again, going through those 4 steps with a little bonus step of that conversion going on, making sure everything's in my base units. So first step, writing things out to the side. Second step, writing out my formula. Third step, plugging in. Fourth step, final answer with units. Okay. All right, we have 2 questions left. If you are feeling fairly comfortable at this point, I want you to go ahead and pause the video. Try the next 2 examples. Once you are done, unpause it, watch through, make sure you've had the exact same steps that I do. Because your work is going to be super important when we do all of these equations. You have to show every single step, just like I show you in all of these videos. But give it a go. See if you can do it on your own. Come back once you're ready, and then we'll do it together. Okay? And pause. And unpause. Welcome back. Whoop, whoop. So, in this example, it says, how long will a 100-watt incandescent light bulb last if it takes 0.13 joules of energy? Ooh, do you remember from grade 8, incandescent light bulb? Memories. Anyways, so it says, how long will a 100-watt incandescent light bulb last if it takes 0.13 joules of energy? So again, step 1, we are writing out what we know and what we're trying to find on the left-hand side. So we have 100 watts. We know 100 watts. Watts is the unit for power, so that represents the power of my light bulb. And we have 0.13 joules of energy. 0.13 joules. I know joules are the units for energy. And it's asking me how long. Okay. Notice it doesn't ask you directly what time will it last. But when I'm talking in terms of the question, how long will it last, implies my time. And my time, I don't know what it is, but I know my final answer will be in seconds because those are my base units of my equation. Okay. Step 2, we have to figure out what equation we're going to use. Of course, the equation that relates those three values together is this one, but we want to isolate for t. So we are going to make our triangle. Here we can see E is on top of t in my equation, so E is on top of t in my triangle. P takes up that last spot. To get t alone, I'm going to cover up t with my finger. I'm going to look at E and P. E is on top of P, which means E is being divided by P. So I will get T is equal to E divided by P. And that is the formula we are going to use over here. Okay. If you have that rearrangement down pat in your head, again, you don't have to show this kind of side purple work that I just did. But if you want to, again, just do it off to the side. It's totally worthwhile. It's something that helps your brain remember. Then I am so happy that you take part in doing that. Okay. For step 3, we're plugging in all of our values. So instead of E, I'm putting in 0.13. Instead of P, I am putting 100. And our last and final step, I am going ahead, plugging those values into my calculator. 0.13 divided by 100 will give me 0.0013 seconds. Okay, so a very, very, very short amount of time, right? That's not even 1 full second, kind of ridiculous. But that's our final answer, right? 0.13 divided by 100 will give us 0.0013. And we have seconds as our units, and life is good. All right. Last but not least, we have one more question. It's awesome because we are going to figure out this last one together. So here we have a question about energy. And it's a little bit different than maybe some of the other questions that we saw before, but still kind of the same all at once. So we have a small toy, some random toy, and it uses 50 watts in half an hour. How much energy was used in watt hours? Fun little tidbit here. We have this equation. Power is equal to energy divided by time. If I want to get energy alone, I could use my triangle. I have E over T, and P takes the last spot. I cover up E. I get P times T. So I get energy is power times time. Okay. Energy is usually measured in joules. Okay. If I'm plugging in values or units here, let's just strictly talk about units here. Power is measured in watts. Time is measured in seconds. So my units for energy, which are joules, are the same as if I had watts times seconds. And I hope I haven't lost you yet. This one's a little bit tricky to wrap your head around. But watts times seconds is the same as joules. And the way that we know that is because if I just look at my equation, I know that energy is power times time. My units for energy is joules. My units for power, I don't know why I had these here, but I'm going to erase them. My units for power is watts, and my unit for time is seconds, which means my joule is the same as a watt second. Okay. What the question is asking us is saying, well, instead of having our units in watt seconds, which are the same thing as joules, let's have them in watt hours. To have watt hours, I need to have my time in hours. Because if I had my time in seconds, I'd have watt seconds. So to have watt hours, I need to have time in hours. Okay. The only reason we're doing something like this in this particular question is just to kind of plant the seed for when we start doing the cost of electricity. So if you're struggling with this concept right now, I hope it'll make a little bit more sense when we start talking about the cost of electricity, which is our next set of notes. But just bear with me for now. Okay. So what we want to do is we want to have our units for power in watts, and we want to have our units for time in hours. Okay? So that our units for energy can be watt hours. Alrighty. We are essentially going to do the exact same thing as we did in all of the previous questions. Our first step, just like always, is to write down what we know. So we have 50 watts. 50 watts. And watts is the unit for power, so that means our P, or power, is equal to 50 watts. And we have that in half an hour. So half an hour is 0.5 hours. And 0.5 hours is a measure of time. And we want to figure out our energy. We don't know what that is. Energy, not too sure. But we want it to be in watt hours. Watt hours. All right. So before we were talking about how our time needed to have the units hours in order to get to watt hours. We are actually already there, so life is good. Our second step here is we are going to write out the equation we plan on using. And if we look to the right here in the purple, we actually already isolated for E, and we said E was the same as P times T. Step 3, we're going to plug in all of our values here. And just this once, I'm going to plug in all of my units so that we can see how those units work out a little bit better. So for power, we have 50 watts. And for time, we have 0.5 hours, right? Because half an hour is 0.5 hours. When we plug this in, we go 50 times 0.5, half of 50, is going to give us 25. And we have watts times hours, which gives us watt hours, which is the unit, the question asked us for. So our energy is going to be 25 watt hours. Okay? All right. So today we talked about power, we talked about energy, we introduced a new equation, and we did a little bit of work with units, we did a little bit of converting, we showed you this funky thing where energy could also be converted into different types of units, and we just kind of played around with it. So there is a worksheet that I'd like you to give a go. It is a power worksheet. The answer is already posted, or the answer key is already posted online. Give it a go. Show every single one of our 4 steps, every single question. Do your best and ask me any questions if you have them. Otherwise, have an absolutely wonderful day, and I will talk to you soon. Adios!